very far into the semester, it seems to be, from my point of view, going by too fast because it's almost test time. So we have a midterm and final. Although midterm is definitely not really a midterm, it is well before the middle of the term. But it seems to be a convenient place to put it. So, all right, details about exactly when it will be held. So on Wednesday, on the 23rd, I will post it in Canvas and also on my external site by 9 p.m. On the 25th. So you'll have at least 53 hours to get it. Wait, no. 55 hours to get it done. All right. Okay. So I've already posted a practice test on the main page for the course site in Canvas and also on my external site on the lectures page, as well as a solution. Okay. Now, so the way this breaks down, there'll be 5 regular problems. So you remember a format from last semester in 460, so I'm following that. So half the test comes from the regular problems, and then there'll be a lightning round question, although given the duration of the test, it won't really feel like a lightning round because you're not having to really answer that quickly. Questions that are based on the quizzes or the concept checks that you're doing in Canvas. Okay, so about the 10 questions of that form. So the practice part only has regular problems serving as a study guide for that part. As far as a study guide for the lightning round, just look at the quizzes. That's really all the study guide you would need for that. So in class, on the class period, oops, I need to check the calendar here, make sure I have this right. Yes, Monday, February 21st. So I'll devote that class period, not covering anything new, but just review, go over practice problems, handle any questions you have about that. Now, we just finished with the coverage. This is chapter 3, so 3.1 to 3.4. We've only seen 3.1 and 3.2 so far. We'll be doing 3.3 this week. And then I'll cover 3.4. Let me just check the rest of my schedule here. Okay. So 3.4 I will cover next Monday. Next Wednesday, I'll start getting into the next chapter, chapter 5. It's on stationary iterative methods, just to keep moving along the material. But that part, that material will not be on this test. So when you have a chance, take a look at this, look at practice. See if you can work them out using the solution as a guide. And be sure to bring in questions, especially for the review that I'll be holding. You now see that everybody's here in one form or another. Alrighty. Now, focus of this week are on certain subcategories of matrices. Everything we've been dealing with so far is solving A equals B, where A is an arbitrary n by n invertible matrix. But there are certain classes of matrices for which the solution process is more efficient, and we want to make sure to take advantage of that. So, there are two classes of matrices that I'll be discussing. So today it will be banded matrices, and then on Wednesday, symmetric matrices, in particular symmetric positive definite matrices. All right. And we do have a general purpose method. So Gaussian elimination with some kind of pivoting, such as partial pivoting, will give you a solution. But with numerical algorithms, it's not just about being able to solve a problem, it's being able to solve it efficiently. And that's going to be the focus for this week. So what is a banded matrix? Okay, so here's some jargon for you. So that the name comes from this appearance of the structure of a matrix, that all the non-zero entries fit within some narrow band centered on the main diagonal. So a banded matrix has both upper and lower bandwidth. So you have upper bandwidth. Here's the algebraic definition that Aij is 0. So if Aij is 0, whenever j minus I is greater than this value for the upper bandwidth p. And now, a more intuitive definition is that A is upper bandwidth p if any non-zero entries above the diagonal lie within the first p diagonals above the main diagonal. So once you go past p upper diagonals, everything has to be 0. And then similarly, we have lower bandwidth q. Aij is 0 if I minus j is greater than q. So the row value is too large relative to the row index is too large relative to the column index. So again, intuitively, any non-zero entries below the diagonal fit within the first q subdiagonal. Everything below that has to be 0. So then the total bandwidth, which is bandwidth, you just add the upper bandwidth, lower bandwidth, and then plus 1 to account for the main diagonal. So if the bandwidth is less than the maximum possible bandwidth, which is 2n minus 1, then we can say that the matrix is banded. Most cases of interest are where P and Q are particularly small. For example, if P and Q are both 1, and we say A is a tridiagonal matrix, and that kind of matrix comes up in a number of applications, especially those involving the numerical solution of differential equations. Another common case that P and Q are both 2, so then you have 5 diagonals in total, the bandwidth would be 5, so we say that is pentadiagonal. Another kind of matrix that comes up fairly often, where we have a matrix that Q is 0, so that actually means that the matrix is upper triangular, but more specifically than that, P is 1, so there's only one non-zero diagonal above the main one. So a first super diagonal, we call that. And there we have a term for that as A is upper bidiagonal. So let's suppose we are performing Gaussian elimination on a matrix that is banded. Let's take a look at what happens. So here's an example. I'm just using X's and O's to indicate 0 and non-zero entries. So here we have lower bandwidth of 1. So we only have this one non-zero diagonal below the main one. And then here's the main diagonal. And then here we have 2 super diagonals that have non-zero entries. So we go ahead and perform a row operation to eliminate this entry, A21. So we're taking a multiple of the first row and subtracting it from the second row. So what's interesting here is, because of the upper bandwidth, these last two entries in the second row will not be affected because you figure out your multiplier, you multiply the entire first row by it, but with these entries being 0 up here, it won't touch what's down here. So the upper bandwidth is not affected by the row operation that we just performed. And now my first column is done. So because the lower bandwidth was 1, there was only one entry below a diagonal in this column that had to be eliminated. Now we go to the second column. Eliminate this entry, A32. Same situation. We take a multiple of the second row and subtract it from the third row. But again, this entry that's outside the upper band will not affect the entry below it. So then we keep going and eliminate this entry, A43, and then this entry, A54. And this matrix is now upper triangular. And it has the same upper bandwidth as the original. Now, also, because the number of entries you're eliminating in each column is equal to the lower bandwidth, in the LU decomposition, assuming no pivot, L has the same lower bandwidth as A. So right now we're not dealing with any pivoting, we assume no pivoting. I'll talk about pivoting later. Now, the number of entries affected by each row operation is equal to the upper bandwidth. Because, for example, if I go to the beginning, my original matrix, here, what's happening with this row will affect the row below it, but only the diagonal entry is used to eliminate the entry below it. The number of entries here that can make change down below is equal to the upper bandwidth. So that's how many entries are affected by a row operation. So that is why, just as L has the same lower bandwidth as A, U has the same upper bandwidth as A. So both lower and upper bandwidth are preserved in the LU factors. So what's the total work? Recall that before, for the general case, Gaussian elimination takes 2/3 n cubed floating point operations. But now, you're working with n-1 columns. You have at most q entries to eliminate. So the number of row operations you have to perform is on the order of n times q. But because of the upper bandwidth, each one of those row operations does not cost order n operations, but rather order p. So the total amount of work is order n times p times q. So now imagine that the matrix is tridiagonal, so p and q are both equal to 1. So Gaussian elimination, taking order n cubed operations in the general case, now takes only order n. So that's true for a banded matrix in general, a small bandwidth, that's independent of n. That you shaved off 2 orders of magnitude, which is really unusual. And that's something that is very helpful for a lot of applications, such as solving differential equations that we'll get into later on this semester. So first question is about the bandwidth of L and U. Now what I'm going to do is to show you just how much algorithms, Gaussian elimination, forward substitution, back substitution simplify for banded matrix, or particular tridiagonal matrix. What I have here are the original algorithms. So first for Gaussian elimination, forward substitution, back substitution. So that's for a general case. So here we have 3 levels of nested loops, so it's order n cubed algorithm. So now I'm going to strip this down using the assumption of the tridiagonal matrix to see how much show you how much it simplifies. Now, the outer loop doesn't change because we're still working with every column except for the last one. There's going to be an entry to eliminate because of the lower bandwidth of Q. The bandwidth comes into play here. So you're starting below a diagonal and you keep going. So j plus 1, j plus 2, up to, at the most, j plus q, because that's how many entries you eliminate per column. But in this case, q is 1, so there's only one entry to eliminate. So really, I is only equal to j plus 1. That's the only entry in this column we have to eliminate. So I can just get rid of that. So really, we don't even need a loop at all. I can just say I equals j plus 1. This whole part will only run once. So what I'll do is I'll just remove the loop, the second loop. Okay, now I can unindent a little bit. Okay. And then wherever we see I can just replace I, j plus 1. Okay. Now take a look at K. Let's look over K. K starts at j plus 1, j plus 2, all the way up to n. But look at how K is used as an index, specifically a column index. Now, when K is equal to j plus 1, that means we'll have a diagonal entry here and here. And then we have a j plus 1. That is an entry that is on the first super diagonal, so right above it being diagonal, so that's fine. But let's suppose that K is equal to j plus 2. Well, then we have a j plus 1, j plus 2. That's on the super diagonal. Same thing here. Then here I have a j plus 2. When you have a tridiagonal matrix, if the row and column indices differ by more than 1, that entry is 0. So for k equal j plus 2 and so forth, the row operation is not going to have any effect because the entry from row j that it's taking is going to be 0. So there's no need for this loop to run except for the first iteration, where k is equal to j plus 1. So now I can get rid of this for statement also. And wherever I see k, I can replace it with j plus 1, the only value that is needed. The question is about how the algorithm simplified so drastically. All right, now for the forward substitution. Unfortunately, we can't see the whole algorithm here. Okay. Now, we're still solving for all the unknowns, so this outer loop is not going to change. But down here, notice that j starts at 1 and goes all the way up to I minus 1. But the matrix L that comes comes from Gauss elimination has the same lower bandwidth as A. So if the indices I and j differ by more than 1, this entry is 0. So we only need to look at j equal to I minus 1. So I can get rid of that loop. And wherever I see j, I can replace it with I minus 1. Actually, one thing I should point out is I need to be more careful about this because suppose I is equal to 1, then I'd have Li0, and that would be invalid. Now the loop that I had before would protect against that, the loop just wouldn't run. So what I need to do is I can fix this by letting I go from 2 to n. And then for the case of I equal 1, I can just carry that out up here. And then I can fold these two statements together so that yi will be equal to bi. Okay, so that's the whole algorithm there. So because I'm removing a loop, I need to be careful about these special cases, like the cases of the first unknown. Questions about that one? Same thing comes up, back substitution. So here's a back substitution algorithm, general case. But U has the same upper bandwidth as A. That's upper bandwidth of 1 in the tri-diagonal case. So if I and j differ by more than 1, this entry is 0, nothing is happening. So j only needs to be equal to I plus 1. But in the case where I is equal to n, so you have j going from n plus 1 to n. Well, a loop like that won't run. So first time through, I equals n, this loop doesn't happen. So for that reason, the case of I equals n, when I strip this algorithm down for a tri-diagonal case, really should happen separately. So I'm going to have the I equals n case done up here. So x n is equal to yn over u nn. Okay. And then I will start at n minus 1 and count down from here all the way to 1. And now in this loop, I can get rid of the inner loop. And wherever I see j, I can set it equal to I plus 1. And then here, I can just combine these statements just for sake of efficiency. So xi is equal to yi. Okay. And actually, what I might as well do is just think of it as one line. So this whole expression divided by u I not going to be done anymore. So yeah, so just like in force substitution, there's just one line. And we see that all three algorithms only need one loop. So the algorithm, all three require order n operations rather than n squared or n cubed. Questions? operations has now been substantially reduced, there's still one glaring inefficiency with all three of these algorithms. Take Gaussian elimination, for instance. It's referring to a tridiagonal matrix. So it's only looking at entries that are on the diagonal, or in this case, below the diagonal, or above the diagonal. And the rest of the entries are zero. But those zero entries are still being stored because A is represented as a two-dimensional array. Same thing with L in forward substitution and U in back substitution. That's wasteful. So abandoned matrix should not be stored as two-dimensional arrays. You avoid storing of zero entries by representing a matrix using vectors, one vector for each diagonal. So you'll have an n vector for the main diagonal, and then a vector of length n minus 1 for the first sub or super diagonal, n minus 2 for the next sub and super diagonal, and so on. So, for tridiagonal case, I'll use a vector L for subdiagonal, U for super diagonal, and then D for main diagonal. So what I'm going to show you is I'm going to take these three algorithms that still work with two-dimensional arrays for matrices and modify them to use vector storage. So I'm going to make a copy of all three. And put them down here. Now, wherever I see a diagonal entry, like AJJ here, I'm going to call that DJ. And then here I'll have DJ plus 1. So I want everything to have only one index instead of two. Then, this right here, whenever the row index is greater than the column index, that's in the lower triangle. So that would be using L. Now, what index should I use? When you have a subdiagonal, so a diagonal below the main diagonal, it's best to index it using the column index. Why? Because it starts in column 1. It starts in a lower row, but its column is in 1. So AJ plus 1, J will be replaced by LJ. Here is referring to the multiplier, so that that's stored in the lower triangle, so that will also be using L. LJ. So all I'm doing is taking the entries in the original lower triangle, dividing them by the corresponding diagonal entry, and note that's my multiplier. And then that's what I'll use down here. LJ. And then finally here, AJJ plus 1. Whenever the column index is greater than the row index, that is in the upper triangle. So here we have a super diagonal entry. For describing a super diagonal, use the row index because a super diagonal starts in row 1. It starts in a later column, but it starts in row 1. So I'm going to call this UJ. And that is Gaussian elimination using vector storage. Notice that U isn't modified at all. Its access here to perform a row operation doesn't change. So the diagonal changes, the subdiagonal changes because you're dividing by these to get the multipliers, but not U. Same for substitution. There's really only one thing to change. It's this reference to L right here. This is a subdiagonal entry, so we use the column index. let's use Li minus 1. And finally, back substitution. Here I have U and N, so that's dN. Here I have dI. And then here, this is a super diagonal entry above the main diagonal, upper triangle. So here I will use the row index, so that would be UI. And that's it. So now we have Gaussian elimination, forward back substitution, wired up to use vector storage for a tridiagonal matrix. And tridiagonal systems come up fairly often, especially, for instance, differential equations. So that's a very important case to make it as efficient as possible. So questions about how these diagrams work? Now, one big problem with banded matrices, and that is pivoting, that I've deliberately avoided until now. It really complicates matters. Because suppose you have a tridiagonal matrix, then you swap 2 rows of it. It's not tridiagonal anymore. So whatever banded structure you have is wrecked by pivoting. And this leads to an unfortunate phenomenon called fill-in. Fill-in is defined to be the introduction of non-zero entries outside the band occupied by the original matrices, non-zero entries. So what can you do? Because pivoting is still necessary. One modification of pivoting strategies that can at least help the situation is relax the condition for the multiplier. Because in partial pivoting, you're guaranteed that the multipliers will be less or equal to 1 in absolute value, because you're always choosing the largest entry in a column. What if you impose a different upper bound on the multipliers, something larger? So then that gives you more flexibility in choosing which row to swap with the diagonal, or maybe not performing a swap at all. Like, what if the multiplier that you would be getting without pivoting isn't so bad? Then you just accept it. So it's a way to perform less pivoting, have less destruction of your nice banded structure. So it's not really a cure, but what can you do? So that's one thing that's very unfortunate is, and that's why working with sparse matrices. Sparse matrices are defined as matrices in which most of the entries are 0. So a banded matrix certainly fits that description, but there are other matrices that are less structured that are also sparse. And you want to have methods for solving A is equals B that take advantage of that sparsity and don't wreck it, which is what Gaussian elimination with pivoting would do. Or if a matrix is not nicely structured, you have random non-zero entries all over the place, if you just do Gaussian elimination, even with no pivoting, you could lose sparsity and therefore efficiency. So that's why solution of X equals B when A is sparse is still a very active area of research. A professor I know of, Tim Davis, I think he's at Texas A&M now. He's basically responsible for the sparse solvers in MATLAB. So that's his specialty, is solving A equals B when A is sparse, and how to use techniques like pivoting more effectively than in the general case. Okay. So I've actually come to the end. I know we're only halfway through a class period. This is the end of at least the discussion of this part of special matrices, of banded matrices. does anyone have any questions either about this or about any homework problems? I know this is the last class of the day for probably all of us. So. I've heard it said that we recommend in the long class period that after 30-something minutes that you all take a break. Something I have done from time to time, although not as consistently as I should have. So this class, I was like, yeah, we go ahead and do that, but we just all come back. All right, I guess we're on break and not coming back. So. Well, if anyone does have one last question individually, of course, I can stick around for that. But, all right, so positive definite matrices on Wednesday.